Hi, good evening all. I'm Karthikeyan, Product Director for Robotics and Automation Division, Maxway Technologies, Coimbatore, India. Today we will have an interactive session on machine loading and unloading automation in discrete manufacturing. Coming to discrete manufacturing is often characterized by individual or separate unit production. It is not like a process industry where one component is dependent on another. Okay, the units can be produced in low volume with high complexity and high volume with low complexity. These are the two options when we consider in terms of discrete manufacturing. When low volume with high complexity, it results in need for manufacturing that needs to be in a flexible manner. And when it comes for high quality, low complexity, high premium and inventory and lead time are the major factors which plays a major role. The solution to this is to have or implement industrial robots and cobots into the discrete manufacturing sector. Before going to that, just let us have an overview of what is industrial robots and cobots. Industrial robots have been in production or deployed since 1960s itself, but collaborative robots are now become more popular, and more of the manufacturers are bringing them to market. They are gaining advance into the all to the automation arena. See, even now, even it is available like a product, Amazon product. See, I have shown you an example in my screen where the cobots are sold as an commercial available product, and they have even given deals for the day. Say in 16 hours and 29 minutes, there is a deal for this universal cobot. And even they have explicitly given the price as 12.9 lakhs only. So the collaborative robots are now commercially available, which even we can buy and deploy in any automation project, whatever we need to adapt. Okay. One such collaborative robot which is famous is this ABB CRB 15,000 type. There are many other robots. There are universal robots. From the aesthetic point of view, we have this ABB cobot, which is more flexible and having agile structure, 6-axis. And this kind of robots, they have developed grippers for these robots, which are extensive for almost all the automations. Here, every manipulator comes with a standard rating of IP54, and this robot is equipped with Omni controller, which is C30 controller, which is not an open source. It is developed by ABB, and which is a RoboWare. And coming to the specifications, major specification, it will be 5 kgs will be the handling capacity, and reach will be 0.95 meters. Its normal weight is 28 kgs. This is something like a washing machine, which we can order the robot, get it, and we can install on the same day itself by we can install on our own. This is a joint torque which we are in terms of the first axis will have a maximum Newton meter, and every further axis it will be reduced by 20%, so that for the first base it is 175 Newton meter, and coming to the last axis it will be around 9.2 Newton meter. And this cobot has a working range. Everything will be in degrees, so 180 degree. This will be in plus 180 degree to minus 180 degree. And axis 2, it will be again 180 degree plus and in minus also. In axis 3, this axis, it will be from minus 225 to plus 85 degree, due to the limitations that we cannot go beyond this axis 2. and axis Y it will be again plus or minus 180 degree, and axis it will be 270 degree, which has end effector due to the end effector limitations and wiring constraints. It is limited to plus or minus 270 degree, which is nothing but 0 degree to 270 degree. And one more thing about this wall mount robot is it can be mounted in a wall in a vertical direction or in a horizontal direction, or in modern machines we can employ this robot, mount this in a place where human cannot enter, such as it can be installed in a cell. Okay, this will be a typical working range where the radius of 951 mm is the operating range maximum, and the footprint is about 200 mm. Okay. And coming to this Berger's manufacturing autonomy model, this is actually a benchmark where we can have the level of automation defined. Level 0, this will be complete manual operation, and one which will be CNC machines or any other machines which process the workpiece in a single stage. And what happens is when we implement these cobots for robots for this material handling, then we achieve the level of 2, which is our target level of automation from 1. Say it will handle the workpieces individually, but it will not have any communication between the to and fro machines. For example, roughing and semi-finishing, we don't have any direct contact between the machines. It will be separate. Still it will be separate, but it. Okay. Okay. How do we achieve this machine unloading, unloading? We use the concepts of whatever the available methods, production methods we have, which will be value stream mapping, Kanban, Poke-OK, and Kaizen. All these will be integrated, and as a result, we'll be having an Industry 4.0. So this slide explains what is the current scenario of machine loading and unloading, which is done by an operator. The operator first carries the pallets or raw material from the storage yard. He will move it near the machine, identify the part, then he will program it in the machine, then he will load the blank. Once machining is completed, he unloads it from the machine manually, and then he places it in the finished products bin, and the finished products will be moved to further process. This process repeats again and again until the entire batch is complete. This is the current scenario, which where every operation is manual. Okay. The problems or challenges where we face is unavailability of operator. If an operator is unavailable during the end of the cycle, then the process is getting delayed, reduced overall equipment efficiency. There will be increased in downtime. Okay. Coming to the available options for machine loading and unloading, there are about four types of loading and unloading option provided here. In this scenario, we have twin turn machines which will be having a double spindle, and opposite to that there will be another machine. Then we will be having a robot. The parts in feed the parts are fed in the conveyor. The robot will handle the machine, both the oppositely faced machines, and once the job is complete, with the help of M2M communication, the job completed command is given to this robot. This robot gives an open command to the CNC doors. The CNC door opens. The robot then picks the component and places in the outfeed conveyor line. And the second option will be a top loader type, where the component is loaded from a gantry, and this is one more use case where we have 8 spindles, and these are.
We'll fix the problem within 2 days. We are actually other.
I can't hear you. Hello?
Sorry, sir. Sorry. Go ahead.
Yeah, and there is one more line where we have 8 spindles, and this is also of front loader type. Okay. Coming to the solution for this manual loading and unloading problem, we have a typical solution for this machine loading and unloading. Here there will be a CNC machine. In front of that, we'll be having a robot or cobot. When the parts are heavy and difficult to handle, we'll go for a robot. And when it is a simple product and which can be handled by a cobot, then we can go for a cobot where the interface with the interface are where in places where we need to work with humans, we can employ cobots. Here the benefits are reduced downtime, and lean material handling will be there, increased overall equipment efficiency. As I already mentioned, there will be a M2M communication with the CNC machine. And there will be data flow between the machine and this robot, where the part completed status is sent to this robot, and once the robot receives the signal from the machine, it will acknowledge and in turn gives a feedback to the machine or command to open the CNC doors. Once the door is opened and that signal gets confirmed, the robot does the picking and placing operation, or that is loading and unloading operation. Okay, and in terms of robot, we need to have safety sensors. That is essential and it is a must. In addition to the fences, now people are going for safety zones where we have an ultrasonic sensors which are programmable in such a way that there will be 2 layers. Once an operator enters into this slow zone, its operating speed actually reduces by 50%. And once he approaches or goes near the robot to a proximity level, then it stops. Once the operator just retracts from the robot, then it will restart, but still it will continue to operate in the slow region mode. That is 50% of whatever the speed it is operating. Say if a robot is operating at 10 meters per second, then once safety zone 1, that is the orange color zone, is reached, then it will decrease the speed to 50%, that is 5 meters per second. And once in the yellow zone, it will just stop. And when the operator comes out of the zone, it will just restart and continues the operation. This is how everything works. And we need to, and there will be a safety fences where we can enclose the entire robot in the safety fence. And if we need to say not to allow the operator near the robot, then we can still do the same. Or this is another stage where we can have safety zones such as slowly operate or start to stop. Okay, and coming to this say industry 4.0 thing, the entire architecture or entire system is now in a closed loop. When there is a manual intervention in terms of loading and unloading, again we are not in a position to control the overall equipment efficiency. We cannot issue a command to an operator who will not directly take any commands from the computer. So these kind of robots, when employed, all the digitally managed job cards will automatically give or send a command to this robot to produce more number of components. And actually these commands are from a centrally managed byte factory system, where the actual production is compared with the target production. Once the target production is not achieved, the command is sent to the robot, and the robot will not stop functioning. It is going to continue to operate till the actual production is achieved. And since the byte factory and ThingWorks platform give a continuous data, we will be able to achieve the OEE. And as we use precision robots, the quality will be in very much high. This can avoid the negligence of whatever the humans are right now. They will be causing some of the trouble such as negligence, accidents. That kind of things can be avoided when we go for a robot. So definitely the quality is going to get improved. And maintenance. We're coming to the maintenance part. Uh, the main reason for getting breakdowns is might be an negligence from the operator side. So say for example, if the operator needs to enter a maintenance schedule, then these things are now digitally managed. So we can have an entire maintenance chart, so that for example, if the number of hours a spindle has run, say 5,000 hours, if we need to change the bearings, then we can do a planned shutdown of both the robots and the CNC machine, and we can actually plan a shutdown, and which will stop and which will generate an alarm, so that the maintenance person over there can come and change the bearings or lubricants or whatever the maintenance that can be done. Even the breakdowns can be reduced to a high extent. And since we have the energy analytics software within this ByteWorks factory, the entire factory power consumption can be monitored, where we can reduce the wastes during night shifts and all. Even we can reduce the uh, mm, say we can without the operator, there is no need for any lights. The bay lights are usually will be consuming more power, so we can limit that power consumption using the energy analytics. Here there is a line shown which shows a closed interloop, and this will be an intelligent one. um, and the same data can be had in the mobile phone also. This thing actually, the solution comes with the increased safety, and this will be closed one, and it is intelligent. This is a typical user journey. If a solution like this is provided, then this will be the user journey, where the digital job card management is done. The batch number, type of parameters, everything will be obtained, and this one is an optional. So if we employ a robot machine vision system, then for the particular product, or even if we can scan the code of the particular raw material billet size, then the CNC program can be automatically adapted, and it can be come into operation. And similarly, the robot can clamp the workpiece from the inward flow bin, and transfer the material to machine, and send the command to the fixture for clamping of the part, and it closes the machine. Uh, After receiving confirmation from the robot, the machining starts to take place after, and also the door close signal. Once the component is completed, from the miscellaneous functions, we can get communication to the robot. Again, the robot opens the door with its command, and it picks the component, and places in the bin or to an autonomous mobile robot, which can actually transfer the component from one machine to another machine. Here there are two things optional. One is inward transportation of the material through AMR, and another one will be outward transportation to the to material to other through AMR. Say this will be something like semi-finishing, finishing, and say next process may be grinding one. Okay. This is the total system architecture, which will be a closed loop, and as I already mentioned, this will be an intelligent, since the digital job card, OEE, quality, maintenance, energy analytics, everything is a part of this factory, byte factory, and the job order and batch details will be sent to the machine. Say target against the actual produced. And the same smart factory, byte factory, will control the robot control unit, which gives the job order and batch details to the robot control unit, which is again an intelligent system which controls the robot. This robot actually does the loading and unloading part. As earlier discussed, we have safety gate, which will be a physical one. In addition to the physical safety, we have a safety sensor which has two zones. One is slow zone, and another one will be stop and restart zone. Again, this robot control unit will be connected to the fleet management system, which will be mobile robots. These carry part from one station to another station. Yes, this one will be for the safety of operator. Actually, I mentioned two zones. This will clearly explain what are the two zones and how we can ensure the safety of the operator. First will be a safety fence. We can use this option for a purpose where we shall not have any interference by the operator or person. If we are having, say, unemployed, illiterate persons to handle the jobs, then we can go for a safety fence um, where we can have a safety guarantee. Once the person enters into the safety fence, there will be sensor, and when the gate is opened, the robot will automatically come into an emergency stop or immediate stop. It will restart only when the engineer is supposed to reset and resume the operations of the robot. And second one will be a guarded sensor. Um, where we have two zones. These places actually we can have. Uh, this will be typically a place where we need to have some kind of interference from the machine. Say, for example, if he needs to have a look into the machine, without entering the machine, it is not possible to have ensure the quality of the product that is being machined. In these cases, we can have a safety sensor or sensor zones. Once when the operator enters into this slow zone, it will operate in 50% of whatever it is operating. Then if the operator decides to enter into a start-stop zone, then definitely the robot will stop, and the person over there, he can inspect the component, or he can load the component, or he can reorient any of the component present, or he can see what is the program running. Any inspection that needs to be done near the machine, that can be handled when he is in the stop zone, so that it ensures the safety. This is how we can go for safety of the operator. Okay, this will be a typical team which will handle the project. This will be typical, say, organization structure where we have support, training, deployment persons, design and development persons, and advisory phase. This is a phase usually which does the site survey, what needs to be done, how it will be done. Everything will be defined in this advisory phase. And this will be the team that will be deployed. This will be a typical implementation approach. The first stage will be application requirement gathering. Usually this will be the specification. This will be the result will be what are the robots we need to employ. Those specifications are needs to be derived in this phase. Say what is the requirement, um, how the operator can be employed in some other job, and what needs to be machined, what is the specification, what is the dimension of the product, what is the CNC machine, how it can communicate with the robot, where is the data coming, say actual versus planned, who is planning, how we need to achieve, what is the requirement, how to handle the data. This will be taken care in this requirement gathering phase. And what is the exact requirement of the customer, that will be gathered in this requirement gathering phase. And from there goes to the second stage, where we'll be designing and validating the requirements from the user. Final end user will be gathered, and we'll go for a design phase, where the finalization of the components, say the robot, the communication with the machine, the gripper size, end effector, payload, and what are the reach of the robot, everything will be finalized in this design stage. And we'll go for a FMEA document, where we'll be having all the failures and its effects, which will be studied, and the design will be validated. Once the design is validated, we will go for a simulation environment, where we will be simulating the entire machine, the components and robots, its reach, and the entire, even the plant layout will be simulated. The cycle time will be calculated. Integration with the demo byte factory systems, everything will be done, and the entire work will be simulated, where we'll be having the cycle time and other critical parameters required for the implementation. Then the next stage comes the procurement. We have finalized the design in the second stage, and we have simulated the environment in a virtual space. Once those are complete, then we'll go for a procurement phase, where we buy the robots and integrate with the where we buy the robots, and this is the place where the entire bill of materials will be ordered against the requirement. Once the material is received, then it goes to the fabrication and assembly point, where if some type of assembly is, sometimes assembly may be required. For example, fixing of gripper into the robot, wiring, and the sometimes the fabrication of the pedestal will be there, and sometimes we need to have a gripper to be machined and assembled, so that we can clamp that particular component. Those kind of stages are involved in this fabrication assembly section. And again, the sixth stage comes the test cases and FMEA. Whatever the design, in the design stage, we would have some kind of process FMEA that will be validated here against the test cases. Once everything, every test cases are passed, then it will be deployed in the field testing. For this will be something like whatever the simulated environment, the same works against the field. Once the user is accepted, once the user is accepted and the part is proved, then we can have a go live system, and the support from the robots and smart factory system will be continued till the end of the life. This is how the implementation is approached. And there is a demo which we have implemented in in an industry, valve manufacturing industry. The robot waits till the door is getting open or the component to finish. This is like typically a HMI where the robot is placed in the center and three machines, it is tending three machines. This is actually having two grippers so that the rough component is removed and the finished component is removed and the rough component is signed placed. The finished component is placed in the bin. Then the process is repeated again and again.